to the last talk of today. That is going to be given by Alexander Cerjan from Sandia National Labs, if I'm not mistaken, and with a quite intriguing title, because you tell us that something is not required, which for an experimentalist is always super nice if you don't require something. The title is An Operator-Based Approach to Topological Photonics, Band Structures, and Bloch Eigenstates Not Required. Very much looking forward to it. Please.
Thank you. Thank you, Sebastian. Thank you, Sebastian, for the introduction. I'd also like to thank the organizers for inviting me to be here and for everyone sticking around. I know that I'm between you and food, so I will be mindful of everyone's time. My name is Alex Cerjan. I work at the Center for Integrated Nanotechnologies, which is a Department of Energy Office of Science user facility that's hosted within Sandia National Labs. I'd like to, right at the beginning, just mention that a lot of this work that you're going to see here was performed by my postdocs, Stefan and Khalil, and all of this is being done in heavy collaboration with Terry Loring, who's a mathematician at the University of New Mexico. And then some people paid for this. I'm not sure they knew what they were buying when they bought it, but here we are. Just a shout out quickly to CINT, the Center for Integrated Nanotech. These DOE Office of Science user facilities, there are a bunch of them. You might have heard of the ones that power light sources, for example. But these are all free and available to the entire international community. So if you are interested in anything that is talked about here, or you're interested in anything else that is being done at CINT, you should just get in touch with us. We are paid to work with you. So no funding required. All right, a couple of talks today have discussed topology. So I'm going to give just a brief introduction from a pedagogical point of view to make sure we're all on the same page. Here, I'm going to give an example of a churn insulator. So this is a two-dimensional system with broken time reversal symmetry. If I go about calculating the bulk band structure of the system, I'll see I find two bands separated by a nice gap. If this were 1979, I would look at this and say it's an insulator, and I would move on with my life to another material. Of course, it's no longer 1979. If I look at this, if I then calculate, say, a ribbon band structure, so this system is now infinite in the horizontal direction and truncated in the vertical direction. I need to project my band structure into this lower dimensional momentum Brillouin zone because I only have one remaining good momentum. And there are two crisscrossing eigenstates through the middle. These then are the well-known chiral edge states that are localized to one side of the lattice or the other, and they cannot backscatter. So these are completely immune to fabrication defects. And you can predict these using a so-called topological invariant. You can calculate, just given this bulk band structure, you can form this one integral based on the Bloch eigenstates. And the fact that this integral comes out to be a non-zero value then guarantees, through this principle called bulk boundary correspondence, that these chiral edge states must appear on the edges of your system. There are many good reasons to make photonics topological. We have heard a number of them from Alberto and Sebastian, among others. One main one is topological lasers. These are robust against disorder, have excellent coherence, phase locking, routing of quantum information, certain designs based on the photonic equivalent of the quantum spin Hall effect or the Valley Hall effect are very good at routing circularly polarized light, even at the single photon level. There's also, you can use crystalline topology to create cavities for light matter interaction. There's been quite a bit of work, especially experimentally on this in recent years. But there are some challenges. So where band theory can be applied, band theory is awesome. I want to make sure that this message is not misunderstood. I love band theory. Sometimes I hate calculating invariants with band theory, but band theory is awesome. But there are plenty of places where band theory doesn't work. You can't use it on systems that don't have translational symmetry. So quasicrystals, amorphous materials, you have disorder, you can have all sorts of finite size effects. Say if you want one of these winding edge states that Sebastian was talking about. Your heterostructure can lack a complete or incomplete band gap. So here, band theory is perfectly well defined, but there's no measure of topological protection. Band theory, the topological band theory is based on the idea that if you have a band gap, the invariant can't change without closing the band gap. But if you've got something like a metal that lacks a band gap, you have no measure of topological protection. So you might spit out a Chern number if you can even figure out how to calculate it, but it's meaningless. You might also have a system that's nonlinear. Localized responses break translational symmetry. How are you going to talk about the topology of something nonlinear? And in particular in photonics, we love something like a nanophotonic Chern insulator. So here I'm showing the Boubacar-Conté structure, which is built using a material that is it's built on a material, magneto-optic material, and it has a very tiny complete band gap. So there's been a lot of skepticism about this work over whether or not this is truly topological or what exactly is being observed. But this is the kind of structure that we would in principle really love to have. This would be very nice to apply technologically. And there's no really good theory for predicting finite system size effects. By bringing these corners next to each other, how close is too close for them to lose their topological properties? More broadly, I love a universal framework for topology without band theory. And the argument for this is actually much simpler. If I start with a system that has two different materials with different topological phases, right now, if I want to calculate their topology, I need to work out their band structures, take their band structures and turn them back into invariants, and then I know what's going on. But band structures are just a Fourier transform. I took something in real space, I took a Fourier transform it to get to momentum space, and now I'm manipulating my momentum space description. Fourier transforms don't add or subtract information from your system. You ought to be able to go from structure to invariant without needing to stop in between. So this is what we love. Love to go straight from description, from material to invariant without any layover. And there's a couple of practical reasons for this. For photonics, it's calculating the Bloch eigenstates and their derivatives with respect to momentum is a hassle. It's doable, but it's a hassle. There's some work for calculating these so-called local topological markers or local markers that's been performed in lattices. But these are not general. They're typically just specifically for Chern numbers, and few can be immediately applied to realistic systems. They're really theories that you need to take your system, turn it into a tight binding model, and go from there. And of course, many systems, especially in photonics, are not well described by tight binding models. So what I'm going to show you today is an entirely different framework for calculating topology. This is going to be a local theory based on a system's real space description. It's referred to as the spectral localizer. I'm going to show you how this allows you to predict topology without a band gap and a realization of this in an acoustic metamaterial. I'm going to show you how this can then be directly applied to Maxwell's equations. And at the very end, I'll describe a general theory of nonlinear topological materials. So, and this is, I want to introduce this by going through, we typically think about invariants, topology as being tied to an invariant. A more modern way of thinking about this is topology as a function of Wannierizability. And to explain what I mean by that, I want to make sure we're on the same page of what is a localized Wannier basis. So Bloch eigenstates are inherently extended across a crystal, but sometimes it's very convenient to think about, instead of having these extended waves, thinking about something that is more particle-like. Localized Wannier states are that. So you take a Fourier transform of a specific band with a momentum-dependent phase, and you transform your Bloch eigenstates into these localized Wannier functions. These are no longer eigenstates of your Hamiltonian. They do not have a definite energy, but they have some energy that it represents the average energy of the band. And the reason that these are very useful in topology is because systems, for example, I'm going to focus on Chern insulators for a minute, but systems with non-trivial Chern numbers do not possess a complete localized Wannier basis. So if you have this invariant that's non-zero, and you go to assign Wannier states to all of the sites, the little unit cells inside of your lattice, you'll find that there are some members of your basis set that you simply can't place. Of course, these are the ones that correspond to the chiral edge state. They can't be localized. There's all sorts of theory and prediction on this. But this general principle holds in both directions, that it's an if and only if statement. No localized complete Wannier basis necessitates a non-trivial Chern number. And this works even for other forms of topology. So, for example, no localized Wannier basis that respects time reversal symmetry is an if and only, is directly equivalent to saying that you have a non-trivial K-Neely invariant, which is the invariant for the quantum spin Hall effect. So this more modern version of topology that looks at this question of Wannier-izability, whether or not you can form a localized Wannier basis, is typically now called topological quantum chemistry. And it's asking, if I start with my favorite lattice, can I take my lattice and path continue it to an atomic limit? So I'm going to chop up my lattice into a bunch of little molecules. I'm going to throw all the molecules out to be infinitely far away from each other. Can I take my lattice, commute it to the atomic limit while preserving my band gap and maintaining any necessary symmetries? And if I can do this, it's trivial because the atomic limit is always topologically trivial. And if I can't, there's some obstruction, it's topological. And then I need to go and figure out what that invariant is that is causing that obstruction. And this, in the framework of topological quantum chemistry developed by Bernavig, is something that is answered using the lattice's band structure. They calculate so-called elementary band representations, and it becomes a large graph theory problem. But there's a simpler way of looking at this. Instead of an invariant, you're asking, can the system be permuted to the atomic limit? I'm going to chop all this up. Well, if I think about what this means in terms of operators, I start with my favorite Hamiltonian and position operator. And in the atomic limit, I have a bunch of blocks. And I have a position operator that assigns the same position to each molecule. So what you're really asking from the perspective of real space is, given non-commuting matrices, can I path continue them to be commuting while maintaining something like the same criteria? Something like a band gap is in real space. We don't know about bands, but something like a band gap stays open, and I don't violate any symmetries. And now this is a question of, transform my question of, do I have an atomic limit, to, can my operators be permuted to commuting? And this is a proud question now we can diagnose using advances in C-star algebra. There are two theorems that underpin this. The first is, given two invertible Hermitian matrices, called an L and L prime, they can always be path connected by a set of invertible Hermitian matrices, so long as they have the same signature, which is the number of positive eigenvalues minus the number of negative ones. So these two matrices, of course, they're Hermitian, so their eigenvalues are all real. So we'll plot them on the real axis. They both have 3 eigenvalues above and below 0. They can be path connected. Here, I can't. I have 3 and 3 on one side and 2 and 4 on the other. Somewhere in the middle, an eigenvalue had to cross 0, and at that point, it became not invertible. Okay, fair enough. The second theorem is from Choi. This is much more recent, from 1988. And it says that if R and S are n by n Hermitian matrices that commute, then the signature of this block is 0. Okay. This is one of these standard math things where this is totally opaque, is what they're really talking about. So to put the physics back in, we need to reassign R to be something like our Hamiltonian and S to be something like our position operators, X and Y. The requirement that they commute then becomes the statement that your Hamiltonian and your position operators commute. So this is now, you're recognizing this as the criteria for an atomic limit. And if I plug all this in, just that formula, I construct this 2x2 block matrix. So it's very large, but 2x2 of these blocks. And I'm asking now, if the signature of this matrix is 0 for a given position and energy, the system can be continued to the atomic limit at that point. This is inherently local. I'm going to ask this for each energy and position in my system, if I need to. So this form can be generalized. This is, you can recognize this as tensoring these matrices with the Pauli spin matrices. More generally, this would use a non-trivial Clifford representation. So this extends up to infinite dimensional systems if you want. Different topological invariants are going to be given by different ways of slicing and dicing this weird operator. So the local Chern number is the signature, but these are all going to be various forms of the original invariants proposed by Kataya. Yeah, sure.
So very nice question. What means that matrices can be connected?
It's just that picture that I had up before, where you have the eigenvalues on either side, and you're asking whether or not there's a path that draws all the eigenvalues together that doesn't cross 0.
But does it mean some variation of coefficients in these matrices?
Sure. Yeah, you're going to take them all and you're going to tweak them. It's going to change your spectrum. Yeah, yeah. But you're asking just whether or not there is such a path that doesn't cross 0. So, which is the crossing of 0 is going to end up being our band gap. So, okay, but so we have Chern numbers or things like winding numbers, which are going to be signatures. We're going to also have things for Z2 invariants that look like signs of Pfaffians or signs of determinants. I'm not going to talk about those today, but they're perfectly well defined. And we get something that looks like a local band gap. This is the minimum, this is the eigenvalue of L that's closest to 0, or maybe the smallest singular value, if that's a language you're familiar with. And so that's just, if we go back to this picture, it's the distance of the eigenvalue that's closest to the real axis. And for a standard toy model, you can rigorously prove that any perturbation whose strength is less than this gap cannot change the local topology. This just follows from the very standard things you know about Hermitian systems, Hermitian operators. So what does this look like? Just some very basic picture. If I take a trivial material, a trivial insulating material over here on the side, and I embed a Chern material in the middle of it, I can calculate the local density of states and their common band gap, and I see a bunch of chiral edge states. When I calculate this that local gap, that quantity mu, I see that it's closing, and in the middle, I find that I have a signature that's non-zero. So everything is consistent. It's simply a local picture of what's going on. You can prove that this local gap closing necessitates the appearance of edge states. So in fact, actually, it's a much easier proof than proving bulk boundary correspondence in band theory, because you're already stuck in real space. You already can see states. But yeah, so this theory has inherently built into a bulk boundary correspondence. These gap closings necessitate the appearance of states in the Hamiltonian. So, in summary, we have a real space approach to topology. It's going to give us local markers for any physical dimension and a local measure of protection with built-in bulk boundary correspondence. This has been developed. There are some math papers that were done by Terry Loring and Hermann Schultz-Baldus. The best estimates we have for bulk boundary correspondence are in this last paper here. To connect this to experiment briefly before moving on to photonics, to show something about how this is going to give you something, maybe a more novel approach to topology, we can imagine stapling an SSH system to a metal with some monatomic lattice. It's going to create a gapless system. You're going to calculate topology of a gapless system using band theory. You can observe that there are states in the system that look like they're topological. They're domain boundary localized or edge localized. And now we can actually not just prove that they're topological by calculating the spectral localizer, but as the localizer is a Hermitian matrix, we can actually take that and have it be the Hamiltonian of some perturbed system. So we can just take our system and probe at different locations for different choices of X here by just rearranging our metamaterial to put different potentials on each lattice site. And so you can actually directly observe this local gap in the system here. So both in simulation and in experiment, here are these two red dots, proving that this system actually has 4 topological states that are all associated with changes in your local index here. So as we sweep across position at a fixed energy, we can see that the index shifts 4 different times, corresponding to the 4 different states I showed you. And you can develop a measure of the protection of those systems, all in a system that doesn't have a band gap. Okay, so this is a conference on polaritons. I should tell you about photonics. This approach to topology is immediately applicable to Maxwell's equations. I need to start with my Maxwell's equations. I'll take the 2 that matter for non-zero frequencies. You can recast these as a generalized eigenvalue equation. This is a pretty standard manipulation of Maxwell's equations. So here's our generalized eigenvalue equation. You can turn this into an ordinary eigenvalue equation by symmetrizing how you treat your vector. And then we can put this on a Yee-grid, say, for example, or at the end, I'll show you how we do this with a finite element method. We obtain a lattice with an effective Hamiltonian. Position operators are simply defined by the vertices, the locations of the vertices in my discretization. And these, I should note, these are just diagonal matrices. They're really easy. So don't get confused by that. And directly then just insert this into the spectral localizer formalism. You can prove that this reformulation actually maintains any symmetries in your system. So for any unitary or anti-unitary symmetry U, if it commutes with our dielectric distribution, which is given by M, the square root of M also commutes with the same symmetry or anti-commutes. And numerically, I would want to point out that this kind of system in photonics would be impossible to do this for local markers that involve projections, which is basically every other theory of a local marker. The problem with projections, projectors onto some occupied subspace, is that they start with sparse matrices and they make them dense. And you have a lot of you have a lot of vertices in a Yee grid discretization of your system. So you started with something sparse, even if you're projecting it to half the size, you're screwed. But this formulation preserves sparsity. So if you started with sparse matrices, this is still basically equally as sparse. And so, for example, just to get a warm up now, we've got our standard Haldane and Ragu photonic crystal. So this is a two-dimensional topological insulator. It's you can observe directly, it has a topological band gap when a magnetic field is threaded through it. You can see these chiral edge states in its transverse electric modes. The TM modes are non-topological. And you can just take this finite piece of the crystal bounded by a perfect electric conductor, stick that right into the spectral localizer, and see, okay, so this is now on the same scale as the finite sample. You can just see as you scan inward that there's a gap closing, and in the middle, that there's a non-trivial local churn marker. You can see the eigenvalue of L that's responsible for this change here, crossing the zero axis, which is what's changing the signature. And if you do the corresponding calculation for the trivial sector of the system, all the eigenvalues stay neatly partitioned on the two sides of zero. You can use this now. Let's put a boundary with some other piece of photonic crystal that's just a trivial insulator. So now we can directly see, okay, we got the topological bit on the bottom, nothing up top, that's trivial. You can even do this for gapless photonic crystals. So here is again some system that is broken time reversal symmetry. And there are some, if we calculate the band structure in the regions of interest, you can see that there is no complete band gap in the system. And yet the localizer pulls out the fact that there's non-trivial topology. If you tried to look at the local density of states in this, you'd see nothing. There's just a bunch of bulk states all overlapping with one another. But you know from the calculation of the local gap that there's a zero all the way around the system, which guarantees you something like a chiral edge resonance in this system. So you could imagine building something like a gapless nonlinear topological laser. So you can take advantage of that resonance, even if they're, it wouldn't be useful for transport because it could backscatter, but there's still probably a high key resonance along the edge of the system that would be perfectly suitable for a LASIK node. So there's another way to look at this. So gaplessness appears in photonics in the second way. This is, you might call a subtle problem in photonics. The original realization of a churn insulator was in microwaves. This is nice because they're surrounded by metal, and the metal for that frequency range acts as a perfect electric conductor. So if I have some material and I have some edge state, the edge state stays perfectly confined and the outside is a perfect insulator. This is not true, really, in, say, the kind of classic topological insulators that we have in the literature. So say the chiral waveguides by Mikhail Rexman or the ring resonators from Mohammed Hafezi. These radiate in the in-plane direction. You could make this as perfect as you wanted to, and you still have bending loss. The same is true here. So what you don't have is a topological insulator bounded by a trivial insulator. You have a topological insulator bounded by free space. Free space is gapless. So what is your measure of topological protection when your heterostructure doesn't have a band gap? I'm not questioning these experiments and their observation, right? We've seen the chiral edge states. That's unambiguous. I'm just saying that we don't actually have a proper theoretical description of what's going on because the exterior material is gapless. So if you really want it, this is the situation you'd like to have, and this is the situation we do have: a gapped material bounded by a gapless one. But no problem for the spectral localizer. The point is that the spectral localizer can have a gap even when the underlying system does not. So let's take another Haldane and Ragu photonic crystal. We'll bound it by free space and surround it in an absorbing boundary condition. So in this case, some sort of PML. We can see that there's a chiral edge state. We'll probe it in the topological band gap. We can see that there's a chiral edge resonance of the system. It's radiating off into space around it. That's clearly visible. But stick this in the spectral localizer, calculate the gap. We see that it closes. We can find the eigenvalue crossing. We can even get a measure of topological protection. It's less protected than you would predict from the bulk band structure of the interior, but there is still protection there. So everything is fine and good. And now we can describe what happens when you embed a topological insulator in free space. The protection is given by the distance of the smallest eigenvalue from the real axis. So in this case, it's this gap. It's about half of what it is in the middle. So it's less than you would predict just from the bulk band structure of the insulating material itself. We can do this for crystalline topology. So even though for classes of topology that exist outside of the 10 Altman-Zernbauer classification, so here's this standard woohoo model that has been realized in a few different experiments. We can define something like a reflection winding number. So it's a little different from a symmetry indicator invariant because it's not a Zn invariant. This is a proper Z invariant, whatever mathematical protection you would associate with systems with chiral symmetry. This has exactly the same mathematical protection, which is not entirely true of symmetry indicators. The biggest problem with symmetry indicator invariants is they don't show you edge states. You know that there have to be misplaced corner states or edge states with symmetry indicator invariants for crystalline systems, but you're not guaranteed that they appear in any sort of common bulk band gap. They could be anywhere. But here, because we have a local marker, we can now scan in energy. We can see 1, 2 gap closings corresponding to 1, 2 changes of our local index. And if we calculate the LDOS and look at the nearest eigenstate in our Hamiltonian, we can immediately distinguish these modes are topological with respect to this reflection symmetry. The system is symmetric about here. And we can even, there's a bit more I can say about this, but I don't want to take up too much time. But yeah, so now you have a theory of topological crystalline systems that will pull out, is immediately applicable with any bulk boundary correspondence.
Yeah, 5 minutes, by the way.
Yep, we're in the last couple slides.
That's right.
Yeah. So, okay, so the last thing I want to talk about is a general framework for nonlinear topology. So again, I'm working in a real space. I don't have band structures. I don't need Bloch eigenstates. I don't need to project onto some occupied subspace. So we can handle spatial nonlinearities for free. All you need to do is take your favorite nonlinear Hamiltonian, pick your favorite occupation of that, psi, stick it into this localizer, and calculate your favorite invariant. So in this case, we're going to go back to Cerjan numbers. We'll use some on-site nonlinearity. So here in the trivial system, if we have an unoccupied lattice and we probe in the band gap of the Haldane model, we'll see that it's topological everywhere. We can also map that out in energy. So you pick some slice through the middle of the structure. You can see that here, this dashed line, this dotted line is showing the extent of where the bulk bands terminate. The topology penetrates a little bit into that region. And we can pull out the protection of that. Okay, standard, I showed you this on the first couple slides, but I can now pick my favorite soliton occupation. So this is some self-consistent solution to this eigenvalue equation. This is what it looks like, and it's very bright in the middle. And that intensity is changing the local topology of the system. It is forcing these few lattice sites to be no longer topological. We can see that also in the plot of the topological index with respect to energy. It's creating its local topological protection. You can prove that this topological protection actually means that even against perturbations, the soliton still has to exist until a perturbation is added that is sufficiently strong here. So you're not just getting protection of an edge state, but it's actually guaranteeing the existence of a soliton in your nonlinear eigenvalue solution. This same theory can be used to work out topological dynamics. This is a model that everyone should be familiar with. It was originally performed by Daniel right here. The idea is that you're going to, again, take a Haldane lattice. This is going to be a saturable gain or a saturable media kind of nonlinearity. We'll have a source and a monitor point over here. We'll drive this lattice with some system, standard evolution at different powers, different choices of how much intensity we're going to scale this by. If you look at the time domain calculation here, you can see that you're, as a function of time, you start to excite the system. You excite this edge localized state. That edge localized state starts to propagate around the system and stays relatively coherent. And so at the time, what was concluded is that this is some edge localized soliton-like feature. They are very careful not to describe it as topological because using band theory, how would you describe this as being topological? You have an excitation that is maybe 6 lattice sites long and 1 lattice site thick, and how would you ever figure out using a band theory what is the topological invariant of this? But we have a local marker. The local marker has perfect resolution. So we can now monitor as a function of time, this soliton picking up a local index as it becomes strong enough, watching that local index follow this edge localized state as it propagates around the lattice entirely. So this is really, we can use this to numerically observe topological dynamics in the system. And as a function of different input powers, you can see that for when not enough power is put into the system, this behavior never occurs. You never, there's some threshold power beyond which you will actually be able to call this a real topological soliton. So finally, the spectral localizer framework is portable. We can do this for your favorite photonic structure. So here's some sort of generalization of the Haldane and Ragu photonic crystal to a quasi-crystal using magneto-optic material. Here's its finite element mesh, and we can pick up this index shift. And at this point, I would say this is a conference on polaritons. If you have a system that you think has smelled like topology, but you couldn't figure out its band structure, or otherwise it was something that was a frustrating experience, you don't have to do anything. This is about 30 lines of code that you add to the end of a console, not even the end of the console simulation. You just need the mesh. And then you use console's features to pull out the various operators. There's some headache involved in doing that, but Stefan's already figured that out. So if there's something you think that you have that's topological and you haven't been able to prove it, we should talk. All right, so I want to conclude. Topology can be diagnosed using an operator-based framework. No band structures or Bloch eigenstates required. It predicts topology in gapless materials, can be directly applied to photonic systems, and it yields a general framework for nonlinear topological materials. Thank you.
Thank you for the nice presentation, and we have actually quite some time. So, Sven,
Thank you. This was too much to digest everything. Thank you very much. Anyways, for the nonlinearity, which you can very nicely add. Can you think of a structure which is trivial, but by nonlinearity you make it topological? For instance, I think that people have looked for that long. I mean, there was Alex Sammeit's paper and so on. And so this is just theoretical, right?
This is so this is the theory, but this is pretty equivalent to what Maxwell has realized, for example. So they had an edge propagating soliton in a lattice that was, the interpretation has been that the soliton creates its own topological bubble and then kind of is its own chiral edge state.
So who demonstrated that?
Maxwell is PRX in 2021.
Okay, then I missed that one.
Yeah.
Okay.
So yeah.
So I'm trying to understand if what this protocol is called is for your calculating this topology. Is it not? It's not just counting the number of modes that cross the gap. It's not just that.
Well, it's slightly different from that. So you have 2 copies of your Hamiltonian. So it's not just looking at states of your Hamiltonian. It's somehow it's looking at the spectral partitioning of this kind of meta operator. But yeah, I mean, that's all it's doing.
I asked this question because recently we have been doing a lot of simulation of valid Hall crystals, photonic crystals. And if you look at the literature, people sometimes find several modes crossing the gap. Okay, not only one, but several modes. And some of them, they say, this is topological, okay, because when I make a corner, it goes around. This one is not, because when I make a corner, it just back scatters. So, do you have any comment on this kind of
You're going to get me in trouble. The Valley Hall, as you all know, Valley Hall is a very weak form of topological protection. So, and there isn't even an invariant associated with it, right? That's not what the old ones are about. You can. We haven't, it's not published yet, but you can put together something that would diagnose something like a Valley Hall phase. It's not quite, I mean, we don't know about K and K prime. So speaking about valleys in this perspective is a little, that part of it is tricky. But if you think of them as crystalline topology, fine, we can do that. So yes, in these cases, it would be entirely possible to figure out if all three of them are topological and just have bad properties, or is it one of them is.
So what does that mean in your framework, that properties? It means that this index, the topological protection that it distance to 0 is very small.
That would be, it's not very protected if that was the case. I mean, there's a more general, I mean, if you want to use these states for transport, I mean, I can tell you that the state exists and the state is topological, and still might backscatter like crazy, right? Because there's a kind of, I mean, those Valley Hall states might be perfectly good Valley Hall states, and they just backscatter because there's an available channel.
Okay, sorry.
Yeah.
Can you be more clear? Are they topological according to your
Valley Hall states, the general Valley Hall state is topological according to a number like this.
Okay.
That is, that's what you want. That's the answer.
Okay. Yes.
Yeah, thank you for the nice talk. So this framework is valid for non-Hermitian systems as well?
Okay, yes. So this is a non-Hermitian system. There is an appropriate generalization. I actually haven't put the equation here for how you would do this. It's not hard. We only have that generalization specifically for Chern numbers. Non-hermiticity from an algebra perspective, a matrix perspective is terrible. Breaks every single property you love about Hermitian matrices. You lose Lipschitz continuity, you lose all the other things. So anyway, the mathematicians implore me to tell you that this is a challenge.
And just to make sure that I understand, so when you calculate these markers, you always fix the boundary condition.
Yes.
So the markers also in the same boundary condition as the districts. So
Yes. Yeah. You pick. Which way to go? You just pick a Hamiltonian, right? Hamiltonian has everything baked into it, right? So your material, in a photonic crystal, an absorbing boundary condition would be baked into either your description of the derivative, if you're using a stretched coordinate PML, or your definition of the dielectric and permeability, if you're using an absorbing layer. That gets baked into this formulation. Let's go back one slide. That gets baked into your definition of mu and epsilon, or your derivatives, which then feed directly into your effective Hamiltonian. So you pick one Hamiltonian, you do everything with it.
One last question. I'm sorry, maybe we in the back. Yes, you already raised your hand.
So, we technically use to find non-trivial topology in the continuous medium,
Do you mean continuous different from Maxwell's equations?
and like no lattice at all.
Sure. Yeah, I mean, right now, okay, let me be a little more specific. We need finite matrices. So if you have infinite matrices, again, certain properties of operator theory start to disappear. Infinite, we are working on the theory of that. Again, the mathematicians would implore me to tell you that this is very hard. In practice, if you have a continuum model that you can perform your favorite discretization, even if it's very dense on, yeah, everything works.
This was a very quick question. We have one more question.
Thank you for a very nice talk. I have a question if there is any relation between the topology of the oracle and the number of its eigenmodes.
Number of its eigenmodes. I'm sorry, I don't, how many?
If you consider weak excitation on the background of the oracle, you can find this, you can calculate the spectrum, and it has a discrete and continuous part. And so we have some discrete eigennumbers, and I'm asking how the number of, if the number of these discrete eigenvalues related to the topology of the oracle.
Not that we have found, we found it's just determined based on the spatial profile, but we might not be looking at the right systems either. So that's a jury's out.
Thank you.
Yeah.
All right, let's thank our speaker and both speakers.